Or should I start? Or?
1 second, sir.
Yes.
Okay. Good afternoon, everyone. Welcome back. So, after a very intuitive and lovely lecture delivered by Professor Sujay Ashok of the Institute of Mathematical Sciences, Chennai, on the principle of least action, we now continue this trend in a lecture by Professor Xavier Viennot of the CNRS, the National Center for Scientific Research, France. So, Professor Viennot is a researcher and the emeritus research director at the CNRS Library Bordeaux. He obtained his PhD from the renowned University of Paris in 1971. His research interests are primarily in enumerative, algebraic, and bijective combinatorics, and its applications to both pure and applied mathematics. He founded and directed the reputed Bordeaux School of Combinatorics, France, in 1980, and has been the director for at least 20 years. His research includes, but is far from restricted to applications of combinatorics in pure mathematics, including Q-series, orthogonal polynomials, theoretical computer science, including algorithms, automata, and language theory, computer graphics, control theory, theoretical physics, molecular biology, and many more. He's written 2 books and published many papers in his illustrious career as a researcher, during which he has given hundreds of conferences in dozens of countries all over the world. He has also held various visiting professorships in many countries. He is actively involved in the popularization of science and mathematics, specifically through the bijective paradigm in combinatorics. Today, Professor Viennot will take us all through an exciting journey through the evergreen art of bijective and enumerating combinatorics using binary trees. So over to you, Professor Xavier. I really hope all of you enjoy.
So thank you very much for the invitation. Welcome everybody to India, and we will talk about the beauty of trees and enumeration and bijective combinatorics. So in nature there is many trees. Trees are everywhere in the landscape, and so we want to give a mathematization of trees. So this is coral. You see, it's not only our electrical discharge. This is branching structure, ramified pattern. Or here is an egg, or here is lung in your chest. Or this is river network. It's a hydrographic network. So all this is branching structure. It's kind of binary tree. So this is on Mars. This is on Earth, on the beach. So this is the same branching pattern on Mars and the Earth. And here is near Bordeaux. This is the Atlantic Ocean. This is Arcachon Basin. This was the beach where the picture was taken. But you need deep inside the water, there is again a branching structure. Trees are everywhere. Even in the leaves, you see, there is a branching pattern inside the leaves of a tree. So mathematics is to give a mathematical abstraction of trees and what it's. So when you look at trees, this is a tree designed by a kid. You can, let's forget the fruits. Let's take a more geometric trees, forget the shape of the bark and forget the geometry, the width, forget everything. When you forget everything, but what you remain is an abstract tree, the mathematical tree. So this is called a binary tree. And usually we take off, we don't put this. So this is the image of a binary tree. So binary trees are everywhere in computer science. This is a famous computer scientist, Don Knuth, and he says that he have written the art of computer programming with 5 volumes, and everywhere there is trees, binary tree in computer science. So what is a binary tree? Mathematical definition. So here is a kind of a definition of a binary tree. This is the image of a binary tree. So a binary tree is a triple where you have a left subtree, you have a root, and a right subtree. So this is the root of the tree. You see, there is a vertex. Here is a left subtree, and here is a right subtree. And maybe you are not used at college with recursive definition, because left subtree is again a tree. So again, it's a root, left subtree, right subtree, etc. And then you finish with a leaf or external vertex. So here is external vertex of the tree, all this when you stop the recursive definition. So, but if you don't understand really recursive definition, just keep in mind the image of a tree like this. And we distinguish left and right. If I make a mirror image of this, it will not be the same binary tree. So this is internal vertex and external vertex. So this is example of enumeration of tree. We want to count how many such tree with n vertices. For n equal 1, there is 1. Then there is 2 trees with 2 internal vertices. Then there is 5 trees, 1, 2, 3, 4, 5, 14 trees. So this is the sequence of number of trees. And we want first an exercise, easy exercise. If a tree has n internal vertices, then there is n plus 1 external vertices. So give a proof of this. It's not too difficult. So let's see the number of binary tree with n internal vertices, or conversely, n plus 1 external vertices. And there is a recurrence relation. If you want to count the total number of trees with n plus 1 internal vertices, because of this definition, then there is a choice on the left, a left subtree with I vertices, on the right, a right subtree with j vertices, and the sum I plus j, total number of vertices of left and right, is going to be n, and so you get n plus 1, because there is one more vertices, the roots. So Cn plus 1, because of this definition, is given by this recurrence relation. And then you have an initial condition. The tree with a single reduced to an external vertex, a single point, is equal to 1. C0 equal 1. And so with this recurrence relation, coming directly from the recursive definition, you can compute the first values, C0, C1, C2, C3, C4, C5, C6. For example, C6 is equal to all this, this product, the sum of all this product, I plus j for equal I plus j equal 5. So you have all, if you know 1, 2, 3, 4, 5, 14, then you get the next one, 132. So by recurrence, you can construct this sequence of numbers, such sequence. So we are going to some easy sequence. So in combinatorics, there is thousands, hundreds of thousands of sequences. And let's try first sequence, well-known sequence, 1, 2, 3, 4, 1, 2, 3, 5, 8, 13, 21. So what is the next one? Everybody guess?
34.
34.
34.
34 because it's
34.
each number is the sum of the two previous numbers. And this is the well-known Fibonacci numbers. You start with the first number 1 and 2, and then each number is equal to the next one, the sum of the two previous numbers. So this Fibonacci number defined by this very classical recurrence relation with initial condition 1 and 2. So this is an image of, in the Middle Age, Fibonacci, the son of Bonacci. It's a famous. Now the next sequence, 1, 2, 6, 24, 120. What is the next one?
720.
720.
Yes, it's a, oh, you're a very good student. So the recurrence relation is an equal n times an minus 1, starting with a1 equal 1. And so this is n factorial. This is 1 multiplied by 2, multiplied by 3, etc., multiplied by n. This is a number of permutation. This is a very common sequence everywhere. Another sequence. I have 3 seconds to start this, to warm up this talk. 1, 2, 3, 5, 7, 11, 13, 17.
19.
19.
Prime numbers.
The prime number sequence.
Non-composite number sequence.
Oh, yes, prime number sequence, it's number which cannot be factorized in 2 other numbers which are different from the number itself, 1 and the number 19. Prime number sequence. And so there is a, so I am sorry because I don't see the screen completely because of the, I don't see the top of the screens. So there is an encyclopedia of sequence in combinatorics. it's we want to guess a formula. How to guess a formula with this is experimental combinatorics. To guess a formula for Cn. So sometimes some famous sequence, the number is going to be a product divided by a product. It's not every second. For example, n factorial, of course, is the product of numbers. Fibonacci is not of this kind, but n factorial is of this kind. So maybe Cn would be of this kind. And then there is some techniques to guess a formula. And so in combinatorics, there is a part of combinatorics which is experimental combinatorics. This is like in physics, where you have experiment with computer, you can experiment and guess a formula. So how to guess a formula for Cn? In the case, it's a product or a product. So we have the first Catalan numbers, 1, 2, 5, 14, 42, the number of binary tree. And then if you take the decomposition in prime numbers, there is some very particular fact which happen, you see. See, there is this number here, there is small prime numbers. If this happens like this, some specialists, combinatorists will tell you, oh, there is a formula, a product divided by a product. Let's take C20. You see, all these prime numbers appear only 1. And this is all the prime number between 1 and the last one, 37. Here, last one is 19. So we guess from this, we guess that there is a formula where maybe there is a product involving 2n factorial. This is n equal 10. All the prime numbers go until 20. Here, all the prime numbers go until less than 40. So we guess that there is a formula like this. Cn equal 2n factorial multiplied by another formula, product divided by product. So let's see what is dn. So dn is a sequence of number. It's amazing that if you, by experiment, it's integer, it's not rational number, it's integer. And then we are going to look in the encyclopedia of integer sequence. Look this encyclopedia. And if you type the sequence, you see you have on the website, there is hundreds of thousands of sequences. If you type the sequence 1, 2, 13, 144, this is a dn, which appear in my experiment. And then you type this sequence, and then it tell you, oh, this sequence is inside the encyclopedia. It's exactly n factorial multiplied by n plus 1 factorial. Oh, so we guess, we discover by experiment this formula. And that the Catalan number is 2n divided by this formula. And so this is pure experiment. You see, so some famous sequences have been discovered this way by guessing that it's a product divided by a product. So let's check. For C4, you have 2n factorial, n equal 4, divided by n factorial, n plus 1 factorial. And so this is 14. So this is called the Catalan number. So the Catalan number go back to see at the 19th century. This is a picture of Catalan, and so we are involved with the binomial coefficient, with the arithmetical triangle. Okay, let me, because I don't see the I don't know what to do. Because I don't see completely my screen.
Maybe come out of full screen. Maybe if you hit your escape button.
No, because I have the small picture of everybody on the top, and I don't see completely my slides.
Maybe hit your escape button, and it should come out of full screen.
No, it doesn't work. Okay, let's continue. So Catalan number is, you can write like this, 2n factorial divided by n factorial n plus 1. So this is the binomial coefficient 2n choose n. And this is very classical coefficient in combinatorics. 2n choose n can be written this way also. I don't see I have a problem with the because I don't see the top of the escape. Oh no.
So maybe you can try sharing your screen again.
Sorry?
Maybe you can try sharing your screen again.
I cannot with escape and okay, maybe like this.
Yeah, this is readable.
No, okay, now it's better for me.
Okay.
Okay, so binomial coefficient. This is a classical formula for binomial coefficient. And you can write like this. So it's a number of subsets having p elements of a set having n elements. So sometimes it's called, this is a notation we have in scientific literature, in n choose p, but maybe in school, in college, you have this notation. In French, you have this notation, but all over the talk, I will take this notation. Number of ways to choose a subset of p elements among a set with n elements. So this is a triangle, the classical triangle of binomial coefficient. And the sum of the integer 1 plus 4 plus 6 plus 4 plus 1, the sum of all integer of the same row is 2 power n, of course, because the total number of a subset of a set of n elements. And this is classical property that this tableau can be constructed by taking, you start with 1, and each time you start with, for example, here, you just take the sum of the two numbers, and it's going to be this one. See, 2 plus 1 equals 3, 3 plus 3 equals 6, 6 plus 4 equals 10, 4 plus 1 equals 5, and then 5, you repeat, 5 plus 1 equals 6. So this is a way to construct the Pascal triangle, or the arithmetical triangle, by taking addition sum 2 by 2. So I say Pascal triangle, because in the Western country, this is well known. It was written triangle arithmetic. It was called arithmetical triangle, but it go back in all civilization in China. You see, this was in the 11th and 12th century, or also in Persia, in Arabic country, and in Persia there was this. Also in India, in fact, in India, Pingala, much earlier, you get also the binomial coefficient. And it's called this number. So let's go back to the Catalan number. Catalan number this is the formula, we guess. We want to prove this formula in this talk. How to prove this? One way is to put the formula like this. And then, so we have a tree, a binary tree, and then n plus 1 times the Catalan number is exactly a choice of an external leaf. A binary tree with n internal vertex has n plus 1 leaves. And then I have 2n elements, and I have to choose n element among 2n. So there must be a bijection between this, the choice of n element among 2n, and then the pair, a binary tree, and the choice of a leaf. So let's check for n equal 2. You have here, there is 6 possible ways. There is 6 subset of 2 elements among a set of 4 elements. So the problem is to find a bijection, a one-to-one correspondence between these 6 elements and these 6 elements. And it is not trivial. It's not easy. It's a difficult problem to find really a bijection between a binary tree where you point one of the external leaf. This is n plus 1 time Catalan number, and here is 2n choose n. So what is a bijection? So in elementary school, you say bijection is an injection plus a surjection. And let's remind you this elementary vocabulary. So you have two sets A and B, and you have a map sending an element of A to an element of B, and an injection. Injection is this is not injective, because this point is reached twice by this point and this point. So this is not an injection. And surjection, this is not a surjection. Every point must be reached by one of these arrows. But in every paper in combinatorics, in fact, we never prove that when you have a bijection, that it's injective and surjective. In fact, I prefer this term of one-to-one correspondence. I prefer this term when you have two sets A and B, A bijection is you pair them 2 by 2. Here is you pair them 2 by 2. Here I have 5 elements, and I have a pairing each 2 by 2. So in fact, in all this talk, in all the paper in combinatorics, when we want to find a bijection, is a map F from A to B, and you have another map G from B to A, and such as that. So if you compose F and G, you get the identity of the set A. If you compose G and F, you get the identity of B. So one of the bijection, there is a reverse bijection. This is the way we prove always we want to construct bijection. And in all this lecture, when I will give you bijection, if you find the bijection, find the reverse bijection, then you are sure it's a bijection. If you have two map F and G satisfying this, then easy exercise shows that this is injective and surjective, both of them. But in all the paper in combinatorics, always we construct F, and to prove it's a bijection, we construct G satisfying this.
Sir, can you please explain the inverse and the identity part once?
So this is you have F going from A to B, and then G going to B to A. And if you compose F and G, it's going to be the identity. If you compose G and F, it's going to be the identity. So we say that one is the inverse of the other. By composition, this is the composition of map. And in all this talk, I will show you a bijection because I will construct both F and G. I don't know if you, is it the answer to your question?
Yes, sir. Thank you, sir.
Okay. So let's give an easy exercise to construct a bijection. Permutation. You know, permutation, it can be viewed as a word. This is a permutation on 5 elements. It's a word with you put in this order 1, 2, 3, 4, 5. You take it's a word 3, 4, 1, 5, 2. Number of ways to do this is in factorial. In fact, also it can be viewed as a bijection. It's a map sending these 5 elements 1, 2, 3, 4, 5. You send 1 go to 3, 2 go to 4, 3 go to 1, 4 go to 5, 5 go to 2. So it's a bijection from a set of n elements to a set of n elements. And it's well known that the number of such permutation is n factorial. And the classical proof. How to prove this? Let's play with bijection and inverse bijection. In fact, n factorial is given by this interpretation. It's a map. It's a map from 1, 2, 3, 4, 5 to 1, 2, 3, 4, 5, such as that. You see, you have a f of I is less or equal to I. So here f of 1 is 1, f of 2 is 1, f of 3 is 3, f of 4 is 3, f of 5 is 2. So each time you have 1 choice, 2 choice for choosing this. There is 3 choice, 4 choice, 5 choice. So this is a natural interpretation of, in fact, of n factorial. It's such function, we call this in combinatorics sub-exceedant function. 1 choice, 2 choice, 3 choice, 4 choice, 5 choice. And then the fact that permutation is n factorial, it means there is a bijection between such function and permutation. So let's do the bijection. So you choose 1, there is only 1 possibility. Then for the 2, I have 2 possibilities. And so I label the cell. There is 2 possible cells to put the 2, and I label them from right to left. So it is first choice, second choice. So tell me the function f, tell me, oh, take the first choice. So I will put the 2 here. First choice. Now for the 3 you have 3 possible choice. So there is 3 possible position. You label the position from right to left, and it tells me the 3, f of 3 equals 3. So 1, 2, 3. So I put the 3 here. I get 3, 1, 2. And then for the 4, I have 4 possibilities. Take position 3. So 1, 2, 3. I put the 4 here, etc. 5. I have 2 possibilities. 1, 2. I put the 5 here. So this is a bijection, you see, between such functions, which are trivially enumerated by n factorial, and permutation. So it depends on the way you label this free position. So this is I claim that this is a bijection, and exercise describes a reverse bijection. You see, if you give me this permutation, 3, 4, 1, 5, 2, you have to construct this function f. And this is the exercise to construct the reverse bijection, which will prove that you have a bijection. So you can extend this proof by, for the number of subset element of a set with n elements, this product, in fact, this binomial coefficient, how to prove this? In fact, this number is the number of subsets having p elements of a set having n elements. In fact, multiplied by p factorial. So n choose p factorial must be equal to this. So what is this? You take a set with n elements. You take a subset with p elements. Here p equal 4, n equal 8. No, n equal 9. And then I take a permutation on p element. For example, 3, 1, 4, 2. I put this permutation on the red point, which is a subset f. You put this permutation. And so what you get here is a pair by a permutation on p element and a subset with p elements. And on the right, you have an analog of the sub-accident function with n choice and -1 choice and -3, etc. So here is an interpretation of this. Here is a pair, which is this, which is the interpretation of this. And you have the equality. You see, this is, you can extend the proof for n factorial to a proof of this. And you get a bijection between this, and you give a proof of this binomial coefficient. So another exercise with permutation, increasing binary tree. So here is a binary tree with internal vertex, external vertex. You are going to label the internal vertex 1, 2, 3, 4, 5, n, such that the label go increasing when you go down. Like this. So each vertex, you see, there is two sons, the left son, the right son, the label go increasing. So you have the label 1, 2, 3, 4, 5, n, going increasing. An exercise shows that the number of such increasing binary tree is again n factorial. It's permutation, in fact. So there is different way to prove this. Maybe you can try to put the 1, put the 2, put the 3, put the 4, and see that each time you have n choice, then n plus 1 choice, or find a bijection. So this is exercise 3. Another representation of permutation is increasing binary tree. In fact, we will use in this lecture some bijection to see the binomial coefficient, the arithmetical triangle, the Pascal triangle or Pingala triangle, to see this as paths. So what is a path? It's a bijection with paths. A path like this, you see, I have a grid. I have a starting point, 0, 0. Here it's a grid 5 by 3. I have ending point. And definition, a path is a sequence of points, tac, 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 like this. Sequence of points. This is the first point. This is vertices, a sequence of points, such that each time you add a new vertex, you go north, you can go to the north, or you can go to the east. So you start from this, and this is another path, you see. Each time you go north, elementary step north, or elementary step east. And then this is another way to see the binomial coefficient, the number of a subset of a set with n elements. Here, so we have a set with the length of the path is 8, the number of edges, 1, 2, 3, 4, 5, 6, 7, 8. So I take a set with 8 elements, and then the bijection between subset and path. You see, this is a subset with 5 elements. 1, 2, 3, 4, 5. So each time you have a red point, an element of a subset, you go east. East, east. Each time you have nothing, you go north. So here is my subset. Here is my bijection. I take, this is in the subset. In the subset, no, I go north. Now this is in the subset, I go east. There is nothing, I go north. East, east. So you have a bijection. This is clearly a bijection between subset and such a path. And the number of such paths is a binomial coefficient I plus j choose I equals 5, j equals 3, so there is 56 such a paths in this grid. And you see now the rule that each binomial coefficient, this binomial coefficient is the sum of these two binomial coefficients. 56 was the sum of 35 and 21. It's obvious when you speak in paths. The number of paths starting from this to this is equal to the number of paths starting from 0, 0 to this point, plus the number of paths starting from 0, 0 to this point. So you get easily this rule giving you the Pascal triangle. You see this 35 plus 21 equal 56 is exactly visualized with paths, which is in bijection with subset. So here is my grid, for example, in my example, and every point you see, I start from this, all this number, 10 is the number of paths going from this to this, 15 is the number of paths going from this to this, etc. 56 is the number of paths going from this to this. The paths always elementary step, north, going and or east. And this tableau, you see, is the same as, it's just a shifting deformation of this tableau. You see, this part, this rectangle in the Pascal triangle is exactly the same as the enumerating path. Now, this is another way, very useful to see binomial coefficient as a certain path. So using this bijection with path, I give you two more exercises. A bijective proof with binomial coefficient. So first property of a binomial coefficient. So if you take any column starting from the top, 1, 3, 6, 10, 15, take any column, you stop somewhere, and then if you take the sum of all this, you get 56. You get this number here. 1 plus 3 plus 6 plus 10 plus 15 equal 56. And so give a proof of this. This is for any J and L. This is in general the identity that the sum of this equals this for a certain J equals 3, and L go from this to this, from 1 to 5. So give a proof of this identity using the path. So let's check what it means. This identity, you see here, 1, 3, 6, 10, 15, 21 is exactly this binomial coefficient here. It's a number of paths starting from 0, 0 and going till this point. Here there's 1 path, 3 paths, 6 paths, 10 paths, 15, 21. And the union of all these paths, the sum of all this number, is going to be in bijection with total number of paths, 56, which is total number of paths in the grid, going to this point. So the exercise is give a proof, give a bijection between every path given by 56 and the union of all these paths, which is correspond to all these points. So this is one possible exercise, playing with paths and binomial coefficient. And second exercise, another bijective proof. So if you take you see, I have 1, 1, take the diagonal like this, anti-diagonal, or 1 plus 1 equal 2. 2 plus 1 equals 3. 1 plus 3 plus 1 equals 5. 3 plus 4 plus 1 equals 8. This is 13. Wow. 1, 2, 3, 15, 18, 13, 21. The Fibonacci number. So it's surprising if maybe you know already this, it's an elementary property, but you get back the Fibonacci numbers. So this is identity. Fibonacci number index n is the sum of all these binomial coefficients, which I can write like this. And the exercise is to give a bijective proof of this by using paths. So how to interpret Fibonacci numbers? I claim that Fibonacci numbers index n, you take n points, and you take a segment, 1, 2, 3, 4, 5, you join all the points by green edges. And I am going to to take what we call a matching of a graph. Is you are going to choose edges, choose the red edges, this one, such that they are 2 by 2 disjoint. So you get a set of, you say, 2, 3 consecutive points, red edges, 5, 6, 7, 8, such that they are 2 by 2 disjoint. And exercise 5 in 2 parts. Question A, prove that total number of such matching, such choice of red edges is exactly the Fibonacci numbers. Or it's easy, you have to prove that it satisfies the recurrence relation. For me, definition of Fibonacci number is Fn plus 1 equal Fn plus Fn minus 1 with the initial condition. And second part of the exercise, if you define A and K, the number of matching of K dimers, number of matching with having K dimers, number of ways to choose to put your dimers or your red edges 2 by 2 disjoint. You put K edges like this on this segment graph of length n. Total number is this binomial coefficient. So you have to find a bijection between such matching with K edges and a subset of K element of a set of n minus K elements. So this is a more or less easy exercise. It's not too difficult. So you prove this. So you prove this fact that the sum of all this. I am not specialist of history of mathematics in India, but my friend Amri in Institute of Math Science in Chennai, he told me about Pingala and you know in Sanskrit there is a short syllable, long syllable. So you see a short syllable, a long syllable, and in fact it seems that Pingala not only a binomial coefficient, but you have some special case of Fibonacci numbers. So it's related, you see, 2,000 years ago. It's amazing. So let's go back to primary school. I have in primary school, you do some exercise, addition, subtraction, division. And I have a long time ago, I have some kids going to primary school and they have to do this homework at home. And it was boring for them to do this. So I show them, let's play with some addition, subtraction, division. Let's play with the binomial coefficient. So let's play with addition. I make them constructing this triangle by each term is given by the sum 15 plus 20 equals this. So you play with addition, starting with 1, and you construct the whole binomial coefficient. Then I told them, let's change the rule. Instead of adding this and this, let's change the rule. So every number, 14, is the sum of this one plus this one. 5 plus 9 equals 14. So you start here. So 1. So you repeat 1. Then 1 and 1 equal 2, you repeat 2. 1 and 2 equals 3. 3 and 2 equals 5, you repeat 5. 1 and 3 equals 4, 4 and 5, etc. So you get a tableau totally different from the binomial coefficient. And then look the diagonal 1, 1, 2, 5, 14, 42. Wow! You get the Catalan numbers. Just by changing the rule of the binomial coefficient, you get the Catalan number. So we are going to give a proof of this in this talk, that we have binary tree. Binary tree are inside this tableau. Now let's play with subtraction, addition, subtraction. So let's take the biggest element in each row of my Pascal arithmetical triangle. So the biggest, and then you delete 2 minus 1 equals 1. 3 minus 3 is 0. 6 minus 4 is 2. 10 minus 10 is 0. So 20 minus 15 is 5. This minus this is 14. Wow! Again, the Catalan number. Just by subtracting. So my kids were going to be really interesting in doing addition, subtraction. And but I told them, if you show this to your master, don't tell her it's Catalan numbers, because she don't know what are the Catalan number and binary tree. But they were really playing with this. And by this coincidence, doing subtraction. So we'll give a proof also in this talk. And then play with division. So we have seen take the biggest binomial coefficient in the even row, and 2 divided by, this is 1, this is 2 divided by 1, 6 by 3 is 2, 20 divided by 4, so you see you have 1, 2, 3, 4, 5, and this is 14. So take the biggest element in each row, even row, or odd row, not the first, the third, the fifth, and take the number 1, 2, 3, 4, 5, 6, you divide, and this is a formula we have seen for the Catalan number. Catalan number is 1 over n plus 1, 2n choose n. So again, you have Catalan number. So easy exercise. Now it's not an exercise on bijection. It's not too difficult. You can show that when you subtract the second fact, this biggest binomial coefficient, you get exactly this number of binary tree. So this exercise is just calculus. If you know the formula for the binomial coefficient, prove this is not too difficult to do this. So let's now give a proof that we get this, we get the Catalan number. I show you the proof. So let's take a grid. You take a diagonal here, and then you take paths like before, the same paths going east or going north, which are below the diagonal, below the blue line. Maybe you can touch the blue line, but you always stay below the line. And such number, you see, in a very natural way, any path reaching here is the sum of the number of paths here plus the number of paths here. So this number, 14, is exactly the number of paths which are below diagonal, starting from this point, with only east and north step. Any path like this is the sum of this path plus this path. So the construction of this tableau is a reflection. It's exactly given by number of paths below diagonal, and starting from this and ending with this, you can touch the diagonal. See, 14 is 5 plus 9. So this is a way of constructing the tableau. 5 plus 9 equals 14. So this is the interpretation of this addition with paths. And now I have to show that such a path like this are in bijection. In fact, it's binary tree. So I just make a rotation. You see the rotation of this path, make a rotation, and it's better to write this like this. You go path like this, you go to the northeast, southeast, you start at the 0 level. You are always above the 0 level. You start from this and then you end here. So it's just another way to look such paths below diagonal, to look them like this, it's better. And my triangle going addition 2 by 2 is now like this, with the Catalan number here. Addition like this, 5 plus 9 is here, 5 plus 9 equals 14 here. So I have, by rotation, I have this tableau. And now I am going to show you a bijection between binary tree and dig path. So here is a binary tree, and I will stop talking. Just look at the video, and the violin will show you exactly the algorithm, the bijection, such that this tree is going to become a dig path. Okay, so the violinist is Gérard Duchamp, and he is also a computer scientist in Paris. And we are in the association Conscience with Mariette Freudenthal in the violin. And you see the algorithm, you follow the tree like this. In computer science, we call this prefix order. You follow the tree, tack, 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 and then each time you have an internal vertex, you go up. Each time an external vertex, you go down. This is a classical bijection between binary tree and what is called dig path. So exercise describes the reciprocal bijection. If I give you the dig path, reconstruct the binary tree. It's a bijective exercise, and you have to understand really the bijection. The video will be on my website and on the YouTube, and so you can, if you don't understand, just look again the video. You will understand the bijection and try to find the reverse bijection. So we go back to the subtraction at the primary school. So we have seen the Catalan number can be described with subtraction. So let's go back to the paths which are below diagonal. And I'm going to show that the number of such paths, which is a Catalan number. Now we know that such paths are given by Catalan number, by the bijection with the violin. And I'm going to show that the dig path, the Catalan number, is a difference between the biggest binomial coefficient minus the next one binomial coefficient. So let's take a path. Take every path in this square lattice. So you take the point path going from 0, 0 to nn. Total number of paths is 2 into n. And number of paths which are below the blue line is, I want to show that we have seen it's a Catalan number. But let's take the paths which are total number of paths. Some paths are bad paths. The paths which are above, they go above the blue line, strictly above. So these paths are going to touch this purple line, this delta line. You see, just above the diagonal, there is this line. So paths which are going to touch, or maybe to cross this line, are bad paths. They are not below the blue line. And so the paths controlled by Catalan number are this path minus the path which touch this line delta. So I have to count what is the number of such paths which can touch the line delta. And number of such paths is going to be exactly 2n choose n minus 1. And how to prove this? Such a path touching the purple line, you define uniquely the point I is the first time you intersect this line. The first time you intersect, so you call this point I, then take the symmetry of this point according to the delta line. So it is minus 1, minus 1. Take this point. And then I claim that the bad paths, like the green path, are in bijection with the path starting from this and ending in NN. Just but the red path here, the bijection, is a reflection. You change this path and take a reflection of this portion of the path according to delta, take the reflection and take the red path. And I remind you, the point I is uniquely defined the first time the green path touch the purple line. This is a bijection, which is the bad path, and such path controlled by this. And so the Catalan number is the difference between this and this. So I gave a proof of this fact at the primary school that the difference between the biggest binomial coefficient is 1 to 514. As soon as I know that the number of paths below the blue line is a Catalan number because of my bijection, dig path, and binary tree. And this is a well-known problem. This Catalan triangle, this bad path, the path below diagonal, there is an extension, the ballot problem. How many such paths starting from this and ending in any point? How many such paths below the diagonal? If the ending point is on the diagonal, then you get a Catalan number. But in general, there is an extension which is called the ballot problem. This was in 1887 solved by Bertrand André. This is a classical. And in fact, exercise 8 shows that the number of such paths starting from here, below diagonal, ending now in any point, where I is this point, I is this number, I minus 1 is this, shows that the number of such paths is exactly the difference between this and this. It's an extension of my proof for Catalan number. In fact, second part of the exercise shows that this equal to this. So this is called the ballot numbers. This was in at the end of the 19th century, an extension of Catalan number. In fact, this number, I discovered they are in a book, they are much earlier in a book by Arbogast in 1800. So here is a tableau of the ballot number. Here is sometimes it's called the Catalan triangle, but so it's much earlier. This number, you see 1, 2, 5, 14, 42, etc. They appear in a book in the Professor in Strasbourg, and you see this is the name year number 8. This was numbering by the French Revolution. It was they give up the classical calendar and they number the year in a different way. So at the primary school, there is division. So we have seen this and the Catalan number, how to prove that the Catalan number equal to this. So to prove like this. But now this is difficult. Maybe if you are very good, try to find a bijection. It's not easy at all. I will not give this as an exercise. And in fact, to prove this, it's Cn plus n times Cn equal this. This is the number of what is called bilateral dict-path. 2n choose n, you see, you can, each time you go like this, you northeast, you take a point in the subset. All the subset of an element of a set of 2n elements are in bijection with such bilateral dict-path. This is counted by 2n choose n. And to find a bijection with this and this is really difficult. It's you take a dict-path, you do nothing, or maybe you choose one of the northeast steps of a dict-path, and you have to find a bijection with this path. So it's not easy. I will not give this as exercise, but another exercise, which is much easier, it's to show that the Catalan number, to prove that the Catalan number equal to this is equivalent to prove this recurrence relation. And if you have this recurrence relation with C1 equal 1, then you get this formula. So I forget to put C1 equal 1 with this recurrence, multiplicative recurrence relation. And I'm going to prove this. I am going to give a proof. So this is the exercise, a small calculus to that this equal to this. And I am going to prove this, the multiplicative recurrence of Catalan number. So let's take a binary tree counted by Catalan numbers. You multiply Catalan number by 2n plus 1. So what does it mean? You have the choice, 2n plus 1 is a choice of a vertex, internal or external. This is internal vertex, or maybe you can choose external vertex. There is n internal vertex and plus 1 external vertex. So you take a choice of any vertex, internal or external, and then take, for example, this choice. You have a subtree here, and then I have to multiply by 2. So twice multiplied by 12 plus 1 plus n. So it's a choice of a tree, a choice of an internal or external vertex, and choice 2 means it's a choice between left and right. I have two possible choices, left or right. So let's take the choice right, for example, among the two choices. And I'm going to make a gliding of this tree. Make a gliding like this. You extend the tree, you see, and then you add a new vertex on the right. And then you complete the tree by adding a vertex on the left with an external vertex. So this is two choice, 2n plus 1 choice, Catalan number, and what you get now is a binary tree. A binary tree with n plus 1, total number of internal vertices is n plus 1, and multiply by n plus 2. And your new binary tree here has n plus 2 external vertex. See, there is n plus 2 external vertex, because the first one was with n plus 1 external vertex. And so this is one part of the bijection. showing that taking a binary tree, choosing any vertex, choosing left or right, gives you this object, which is a binary tree with n plus 1 internal vertex, plus multiply n plus 2. N plus 2 is the total number of external vertex of this new tree. So the exercise is to find the reverse bijection. The reverse bijection, the reciprocal bijection. If you take a binary tree with n plus 1 vertices, if you take choice of an external vertex, there is n plus 2 possible choice, then you must get back this triple, left or right, any vertex internal or external, and a binary tree with n vertices. So this is exercise 10. See, to do the reverse bijection of this bijection. And the interest of such algorithm in computer science is that if you take a binary tree, a random binary tree, random means that any vertex, any binary tree with n vertices, which is counted Catalan number, appear with the same probability, a uniform probability, how look like a random binary tree. Random among all possible binary tree with n vertices, you fix n, and there is here it's n equal 1000, n equal very big, and this is the image of a random binary tree. Each binary tree with 1000 vertex appear with the same probability. And this algorithm, the bijection going from binary tree to with n vertices, to binary tree with n plus 1 vertices, this algorithm, if you take a random binary tree, a random vertex, a random left or right, you apply the bijection, you get a random binary tree with n plus 1 vertices. So it's very useful to get a good algorithm to take random binary tree. But random binary tree, this is a random increasing binary tree. So there was an exercise, increasing binary tree was permutation. So if I take a random permutation, I can associate a random permutation, each permutation appears with the same probability. A random increasing binary tree is this picture, which is totally different from this picture. This is very thin tree, it's very thin, and this is much well-balanced tree. And it's related to, in fact, binary search tree. There was a talk by Meena Mahajan, I think, in November, about decision tree. So this is related, decision tree, binary search tree in computer science, and there is some what we call analysis of an algorithm. How is it going to cost you to construct a binary search tree? Binary search tree is analysis, in fact, is analysis on permutation. Such tree are in bijection, it's random increasing binary tree. And so this is how it look like a permutation when you transform the permutation into a binary search tree. So it's totally different shape, and it's two possible random tree. So this is the first part of the big part, the 2/3 of the talk. It's about bijection and elementary things about binomial coefficient. So second part is about how to relate this with analytic calculus, with proof, and how to relate the classical combinatorial is analytic proof with the generating function. So maybe I don't know if you can stop here to talk about some question, or before going to the second part, which is more higher level. It's or put the question at the end, maybe. Okay, let's go on with now calculus proof, analytic proof. So here the Catalan number 1, 1, 2, 3, 4, 5. So we have seen the recurrence relation. How to prove that it's 1 over n plus 1 here? 1 over this is the recurrence relation. How to get a proof that the Catalan number is 1 over n plus 1, 2n to n. So I'm going to give you the calculus proof, what is called the analytic proof. So take this polynomial. Put some variable, C0, C1t, C2, T2, C2, T3, etc. Until stop until 5. See, I have C6 equal all of this. So take the square of this polynomial. Take the square. So compute the. So you get this plus this plus this. This is the term in T, T2, T3. So this is a product of polynomial, squaring a polynomial plus until t power 10. Because of the recurrence relation, this is C1, this is C2, this is C3, C4, etc. So in fact, you get this part of the polynomial is the same as this part here. See, this is C6, T5, so you get C6, T5. So you have exactly the same, the first term, not at the after, but the first term are the first term here are the same as this. But you have to multiply by t. I should have C6, T6. So I have to multiply by t. And if I take t times this, plus t times this, plus t times this, I get exactly the same as this. So I have this identity that if I call this y, I have not exactly this. I have, this is y2 multiplied by t and plus 1. I have not exactly this, but the first term, all the term of degree 6 in both sides are the same. But after they are not the same, of course, because the coefficient of Catalan number for T10 is not, this is 1. But these two polynomials are the same term until the degree 6. So if you do this for 7, 10, etc., degree 20, so you can go more and more complicated polynomial. And so what we need to have a polynomial, but with plus point. So this is called a generating function. This is called a formal power series. And then this recurrence relation with initial condition will be equivalent to this, where y now is no more a polynomial. It's an infinite polynomial. It's called a formal power series. So let's remind you now, what is a formal power series? So you have Catalan number. You have this polynomial we have seen of degree 5. And the formal power series is a polynomial plus point. So intuitive, if you don't know about this for young students, it's let's just take a polynomial plus point. You can stop it. You can go at any level you want, like this polynomial plus this plus point. This is the formal power series. And then if you have a sequence of number, you can associate this formal power series, which is we call the generating function. So this is one of the key tools, a very important tool in enumeration in combinatorics. Let's play with formal power series. I claim that the inverse of this is 1 plus t plus t2 plus t3 plus tn. Why? It's because if I multiply this infinite polynomial, if I multiply this by 1 minus t, the term is going to cancel 2 by 2 and you will remain to be 1. And so I have this, this identity, that's the inverse of 1 minus t, 1 plus t plus t2, etc. So a little exercise, what is this? 1 over 1 minus t plus t2. So it's going to be, 2, 3, 5, 8, 13, 21, the Fibonacci number. You get the generating function of Fibonacci numbers. And how it works, if you are not used with a formal power series, so 1 plus, you see, you have to 1 plus 1 minus u equals this, t plus t2. So I have to make 1 plus t plus t2, plus t plus t2 to the square, plus t plus t2 to the cube, plus etc. So you have an infinite tableau, an infinite series, but that it makes sense because if I sum here, I have 2 terms, I have 3 terms, 1 plus 3 plus 1, I have 3 plus 4 plus 1. So in each column, you get exactly the Fibonacci numbers. So this power series, this infinite tableau makes sense because in each column, there is a finite number of terms. So formal power series, you can do everything you want, almost everything. Usually there is a notion of convergence. Oh, but if I put t equal in this formal power series, if I put t equal 2, this has no sense at all. But in a formal way, it makes sense if you keep the variable t. So this is making, you are not allowed to do this. T plus t plus t plus t, no. Or 1 plus 1 plus 1 plus 1 plus 1 infinite. You are not allowed to do this, but you can do a lot. You have a lot of freedom. It's a formal way. The generating function is formal. You don't look about the convergence of the formal power series. And then so you can make analytic proof with formal power series. For example, this recurrence relation with initial condition is equivalent to this. It's equivalent to solve this equation. And now I can get the formula for the Catalan number. I am going to solve this. where y is a formal power series. So this is very classical enumerative combinatorics. So to solve this, but in primary school, we know how to solve a second degree equation. Suppose A, B, C are numbers, y is a number. So you know the solution. This is in every elementary book. That's a quadratic equation. If you have some numbers, it's equal to this. So this, in my case, is y is going to be 1 minus. There is a plus or minus, but if I put plus, it's making nonsense at all. I know I have to put minus, and the square root is power 1/2. But we know that 1 plus u power m, this is a binomial, the well-known binomial coefficient. If you take 1 plus u power m, this is the binomial coefficient in the classical Pascal triangle. But I am stuck. What happened?
Maybe just try clicking on the file once and then hitting the arrow. Just try clicking on the file once.
On the what?
Just click on your file with your mouse.
On the which file?
Just click on the screen. Yeah, now try maybe. Yeah, perfect.
Because my mouse is not working anymore.
I think your screen is visible. You have expanded the binomial coefficients.
Yes, okay, the screen is.
Yeah.
And so I have this expansion with m, in fact, m equal 1/2. So it works. I just apply the binomial coefficient in case m is an integer. Just apply it with m is not no more an integer. So m equal 1/2, u equal 1 minus 40. So I have, in fact, an infinite series. I have no more a polynomial where m is an integer. And then if you apply this, solving this quadratic equation, then you get this. And after a few calculus, so forget about the detail, but for m equal 1/2, you just apply the same way for the binomial coefficient with m equal 1/2, and then you get a Catalan number. After a few calculus, you get exactly the expansion with Catalan number. So this is the classical way, you see, to solve, to count binary tree by using a quadratic equation and doing an expansion in the same way as expansion with the binomial coefficient. So this is recurrence relation, generating function. And now there is more. The modern way in combinatorics to do combinatorics is when you have a binary tree, it's a left subtree, a root, a right subtree. It's this design. And in fact, we don't need no more recurrence relation. The modern way is to say a binary tree is else, it's an external vertex plus the product of this by this by this. So we can define the product of two objects. We can define at the combinatorial level, product of object, sum of object, sequence of object, the derivative of an object. So we are at the level of combinatorial object. We have this formula, and then you can project this formula from the binary tree, go to the generating function, and this becomes this. So here there is higher combinatorics. This is a level of analytic calculus, polynomial, formal power series, etc. And this is at a level of combinatorial object. So example, if you have a generating function for certain object A, you have this generating function. So 1/1 minus u is a generating function for sequence of object. We have an object, a sequence of object. For example, take this point object, this, or an edges with a weight t and t2. And so 1/1 minus this, it's a projection of a sequence of such object, sequence of this and this. So sequence, take a sequence, tac, 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 sequence of this, and then sequence of this, you get back the Fibonacci numbers. So this is a modern way, you see, to do combinatorics. We have some operation at the level of the combinatorial object. Product, sum, sequence, even derivative. And when you have this formal calculus on the set of combinatorial objects, you project it at the set of formal power series. So this is just, this matching is a sequence of this and this, the Fibonacci numbers. So this is what I conclusion of the talk, the bijective paradigm bijective paradigm is, before talking bijective paradigm, let's go back to Jean-Louis Lagrange, you see, at the 18th century. This is a mechanic book. And here I say, in this book, on ne trouvera point de figure dans cet ouvrage. You will not find a single picture, a single figure in this book. All this book on mechanics of planet, everything, is with calculus, and he is very proud to have eliminated all possible figures and picture. So at the beginning, at the Greek time, at the Newton time, etc., there was some picture, the tangent, derivative, and then all the picture was eliminated. And now in modern combinatorics, it's a return of the visual mathematics. It's a return of the picture. And so we have seen bijection. We replace calculus by figures in bijection. You see. So this was the Greek time, you see. Proof without word, n to the square equal 1 plus 3 plus 5 plus 7. So the proof of this, you don't need to speak. It's a proof without word. You can see the proof. And a lot of people at the modern time believe that this is only true for elementary identity. No, no. You can give a proof without word, a few words of this identity. This is a beautiful identity. This is a continuous fraction with a variable q. This is a big power series divided by this big power series. And in fact, this is Ramanujan continuous fraction. See, the famous Indian mathematician, he was from Kumbakonam in Chennai, in Tamil Nadu, close to Chennai. This is the famous Ramanujan continuous fraction of the famous Indian mathematician Ramanujan. And in fact, we have a calculus. And when I say transform this into manipulation of picture of figures, this continuous fraction is going to be interpreted by this kind of picture. This is called a heaps of dimers. And there is a weight on the heaps. On each dimer is minus Q2, minus Q3. There is a heaps of dimer with some weight inside the heaps. And then this numerator is going to be, this denominator is going to be interpreted by this, numerator interpreted by this. So the picture, you go back to matching and Fibonacci numbers, but there is some weight on the dimer. So you have to show that this picture divided by this picture is equal to this. And then this is modern combinatorics to give interpretation and then manipulation of picture, of bijection, etc. And here I have a heaps of dimers. See, the dimers are one over another, a kind of heaps. And if I take off, I forget all the variable q, in fact, such a heaps are in bijection with dict path. I have Catalan number and Fibonacci number behind this picture. And I show you the bijection between a dict path. The dict path is going to be rotated and a heaps of dimers. So here is a bijection. So again, Gérard Duchamp. So you see, it's this continuous fraction of this has to be interpreted by visual picture. So the calculus, this big identity, become a result of from the visual picture. So you have both point of view, and this is modern combinatorics. Product of object give you theoretic function. Sequence of object give you, for example, Fibonacci numbers. And we can construct the product of binary tree. It's recent papers as a sum, the product, everything. So you can really make operation on side the combinatorial object. And this is a famous Feynman diagram. in quantum mechanics. This is interaction between particles. You see, this is electron, photon, and look what happened here. It's you have a binary tree, and here we have a sum of some picture. So you see, now this is a new way of doing theoretical physics, combinatorics, etc. It's coming back. All the pictures, bijection, etc., are coming back in mathematics. This is a mathematical of binary tree. So, so historically, Catalan number, in fact, Catalan number, it was in fact it was defined by Euler, a triangulation of convex polygon. If you have a convex polygon, a triangulation, you put some diagonal in blue, 2 by 2 disjoint, and the number of such triangulation is exactly the Catalan number. In fact, this was defined. Catalan number was introduced by Euler in 1751. It was much earlier. So this is a letter he sent to Goldbach, and this is the last page of the letters. So he's counting such triangulation of a regular polygon. You have a regular polygon with n elements, and you put some diagonal in blue, which are 2 by 2 disjoint. You put the maximum possible number of diagonal, and you see here the Catalan number. This is the triangulation. Catalan number here appear. He has a formula for Catalan number of triangulation. Here are the Catalan number, and you see here he has a genetic function, and here the square root. He has 1 minus 2, the square root of this. So he has exactly what we have done. And in terms of, this was in 1751. So at that time, it makes nonsense. This was, some people complain, no, this is make nonsense to have this infinite power series. It's, after it was defined, well defined, but, so he was working with triangulation. And there is a bijection, in fact, between triangulation and binary tree. So this is my last bijection. So in fact, the bijection goes the following. You take a triangulation of a regular polygon. On each triangle, you put a green point, and then you connect 2 green points if the 2 triangles have a common edge. And you see, you get a binary tree. You get a binary tree in like this. And so the exercise describes the reverse bijection. So I don't want to abuse of the time. I have some, to finish some relation with physics. How many times I should?
So I can go for like maybe like 10-15 minutes more if okay for you.
10 minutes?
Yeah, 10-15 minutes if it's fine with you.
Yeah.
Okay, sir.
So the application to physics, the TASEP, totally asymmetric exclusion process, you have a strip of particle, you have a strip. Some particles are moving inside. Exclusion means there is at most 1 particle in each cell. And you choose by random one of the separation. And then you can move the particle with probability 1, or you can get inside with probability alpha, you can get outside with probability beta. And then you want to know what is, after a certain number of time, what is the probability to get such a state, what he calls the stationary probability. This is Markov chain, etc. And what is the probability to get this state? And you see here the probability to get this, or this. So stationary probability means it doesn't depend on the initial state. You have any initial state, you do this movement of particle by random, and after a long time, you have a unique probability, and you see the probability 14 because it's a Catalan number. Wow, what is the Catalan number appearing here? And so the probability to get this is equal to each state. When you have a point, you go up, you associate a path, a point, so up, I go east, up, etc. So to each of these states, you associate a path. And then the stationary probability to get this after infinite time is exactly the number of paths which are below the green path. And total number of such pair is going again to be the Catalan number. So the Catalan number appearing again, you see it's a pair of such paths. There is a bijection with binary tree. And for example, if I take these states, to these states, I associate this path. And now if I want to count the number of paths below this, again, we know how to count paths. We make the sum of the number 2 by 2. And so the probability to get these states is exactly 12 number of total paths below this path divided by Catalan number, which is 429. And so there is an extension with probability alpha beta. Sorry to go fast, but there is an extension with trees. And in fact, if you have probability alpha to get inside, probability beta to get outside, then the probability will be given by you take all possible paths, all possible binary tree, and you count the length of this left branch. Alpha power the length, beta power the length of this right branch. And so by counting the length of the left branch and right branch of the binary tree, you can deduce the probability in this physics model. And this is called the partition function. And the partition function, as is related to this ballot number, appear again in the story. And there is a formula which can be proved bijectively for the probability of this model. Sorry to go very fast, but this is to show you that the combinatorics of path and binary tree give you the solution of this model in physics. And in 3 minutes, I will final surprise that relates molecular biology, computer science, and hydrogeology. There is binary tree everywhere, trees everywhere, even in molecular biology. So RNA, you know, it's very, with the vaccine, the COVID, the virus, there is some vaccine with messenger RNA. So it's everybody heard of a messenger RNA to have the vaccine for the COVID. So here is a molecule, secondary structure of a molecule of a tRNA of a. So if you follow this, you have the primary structure. It's a word in 3 bases IUGC, and this word makes some this picture. This is called the secondary structure of the molecule. So in blue, it's the hydrogen bonds. So this makes a secondary structure, and then secondary structure is going to fold up in the space to have the 3-dimensional structure, which is very important for the function of the molecule. And you see below this tRNA, if you connect these blue bonds, this graph in 2 dimensions, so there is a tree. It's not a binary tree. It's here. It's a 3 sun. It's a ternary tree. But in fact, this is a big molecule, 16S RNA of Escherichia coli. And below, you see, below this molecule, there is a forest of tree. And this forest of tree, some mathematicians have studied to what they want to predict the shape of the molecule when you know the primary structure, and they define the complexity of the molecule. And the complexity is a certain combinatorial parameter on this forest of tree. But forest of tree, in fact, is a sequence of planar tree. Planar tree is a point plus a forest of tree. In fact, forest of tree are counted by Catalan number. There is a bijection between forest of trees and binary tree. And the surprise is that when you transform this, the final surprise is that in molecular biology, you can define the complexity of this forest of tree. forest of tree are counted by Catalan number. It's a parameter Catalan number. Now, if you go back to computer science, to arithmetical expression, there is below the arithmetical expression, there is a binary tree. See, A plus B divided by C multiplied by D plus A. So this arithmetical expression can be transformed into a binary tree. In computer science, there is what is called the minimum number of registers you need to compute the arithmetical expression. So there is a second parameter, totally different from molecular biology. And now the third parameter, the Strahler number of a binary tree, has been defined in hydrogeology to study the shape of river networks. So we have three parameters: the complexity of a molecule in molecular biology, the minimum number of registers related in computer science to a binary expression, the Strahler number in hydrogeology, and these three parameters, they have the same distribution, which means they have the same generating function. The number of binary tree having a Strahler number equal to k is equal to the number of tree with minimum number of registers equal to k, which is equal to the number of forest of planar tree coming from molecular biology with complexity equal to k. And it means that if you take S and k, the number of binary tree with n internal vertices and Strahler number equal to k, you have a generating function. So the three problems, molecular biology, hydrogeology, and computer science, they have the same generating function. And if you look, this is binary tree with Strahler number 0, Strahler number 1, Strahler number 2, Strahler number 3. You have beautiful generating function, very beautiful generating function. And if you take the sum of the coefficient, you get 3. Here you get 21. Here you get 487. So these three generating functions, these three parameters, it's very deep combinatorics. It's not obvious at all that these three parameters coming from totally different science have the same generating function. And if you look, you have F1, F3, F7, F15. And this is again Fibonacci numbers. And if you look carefully at the coefficient, 1, 6, 10, etc., they appear, they are exactly here. This is a coefficient appearing in the denominator of this parameter. So this is very beautiful, very deep combinatorics coming from three completely different motivations, three completely different fields. So thank you for your patience. Thank you very much. So I will put the slides of the talk. I will put on my website. It's Viennot.org, and I will make a special page for the STEM 21, and within maybe next week, or I will give you the solution, or hints to the exercise. And I thank you, all of you, and I wish you have a good study. And this is Sarasvati is a goddess of knowledge, science, art. Here is pure art, combinatorics, and so I wish you success in your study. And thank you very much. So if you have any question.
Wow, I must say, thanks a lot. Words can't thank you enough for this wonderful presentation you have just given. So thank you very much for that. It was absolutely amazing how you actually managed to link seemingly unrelated concepts, like ranging from trees, binary trees, to Fibonacci numbers, to Catalan numbers, to binomial coefficients, Pascal's triangles, and the power series, generating functions, continued fractions, and like the most surprisingly applications to physics and molecular biology. Like it was indeed a marvelous lecture. So huge thanks from all of us to you for that. So thank you once again. So we now open for like a short QA session. So if you have any questions, like either raise your hand and unmute yourself, we'll call out names, or you can post them on the chat box.
Sir, I have a question. In brief, can you please tell us some of the algorithms in computer science that are based on binary trees?
I'm sorry, I don't understand. Maybe this. In computer science, what is the question?
Sir, can you please tell us about some algorithms in computer science that are based on binary trees?
Which have some algorithm computer which have been what? Which have been
based on binary trees. Algorithms in computer science based on binary trees.
oh, for example, there is what's the so-called binary search tree. When you enter a random permutation, then you binary search tree. You have a data structure with n elements, and then you can enter this. Look at it as a binary search tree, which means that if you want to add or delete an element or ask a question, then it will be the cost of the algorithm will be in log n times. And if you want to analyze this log n, etc., which means it's going to be related to what I call increasing binary tree. And increasing binary tree, you have to find what is the average height of the vertex label n in a random binary tree. And this average height will be logarithm base 2 over n. So the analysis of the algorithm, for example, in binary search tree, will be exactly a computation of an algorithm. It will be to compute the average height, the distribution of the height of n in an increasing binary tree. There have been another example is what we call data structure. When you add an element in a data, you delete an element, you ask a question, are you or not in the, so this is called data structure. And if you add, delete, then the cost of this is going to be related to the orthogonal polynomial. So there is a combinatorial theory of orthogonal polynomial, and computing the cost is going to be related to a number of time you are in a dig path with some weight. So it's dig path with some weight, and you have to compute how many times you are at level k in this such weighted dig path. So all this is computing the cost of random insertion, etc., deletion in the algorithm is going to be related to the combinatorial theory of orthogonal polynomial, which are based on dig and weighted dig paths. This is two examples which are. These have been done by Flageolet, Françon, Villemin about 30 years ago. It's a whole theory of
Thank you, sir. Sir, there's one more question in the chat. So how do binary trees show up in Feynman diagrams?
Feynman diagram, oh, it's a whole theory. I'm not specialist on the picture I show you was it was behind this was integral everything, and so there is deep combinatorics behind this. This is all theory. Quantum mechanics is really old, but now there is new way to look at all this quantum diagram. And in Bordeaux, I have a colleague Tanasa who is writing a book on the combinatorics of such a diagram, etc. And oh, there is beautiful deep combinatorics. I cannot give you the detail, but it's really beautiful. So this connection. Even there is a new journal now in Paris, which is called Combinatorial Physics. It's related. It's a real journal, new journal. It's related combinatorics, enumerative combinatorics, bijective combinatorics, and theoretical physics. So there is some exciting relation. Quantum gravity, for example. Also, Feynman diagram is quantum mechanics, but the new physics is quantum gravity to unify Einstein relativity and general relativity and quantum mechanics. And there is some combinatorics appearing in this. Oh, there is much more to say. It's,
Thank you, sir. Any further questions? We are nearing the end of the session. So if you have any further questions, feel free to write to us and we'll get it answered by Professor Viennot. So once again, a huge thanks to you, sir. Like the enthusiasm and like the energy with which you delivered your lecture is something which we really look up to. So thank you very much for that.
Thank you, everybody. Thank you for the invitation. And sorry for some disturbance because my mouse was not.
It was a perfect session. Thank you very much for that.
Thank you so once again.
Thank you very much for your attention and the invitation.
Thank you, sir. So we now meet next at 5:30 p.m. when Professor Srikant Srinivasan of Srikanth Srinivasan of IIT Bombay will be delivering a lecture on Professor Srikanth Srinivasan from IIT Bombay will be delivering a lecture on polynomials, combinatorics, and computation. So I really hope to see you all there, and have a great day ahead. And thank you very much, Professor Viennot. Have a great day.
Thank you.